N symmetric matrix. And we say that the quadratic form is determined by this candidate. That is, this is the function on Rn with values in R, where each x in Rn is sent to x transpose, where x is represented as a raw matrix. Or equivalently heavy, since there is a one-to-one correspondence between them, we will not make any distinction. This negative semi-definite with all x in Rn is a weight x, but that's equal to x transpose is less than or equal to 0. We say that it's positive with all x in Rn. This is larger than or equal to 0. Now, negative definite and positive definite will correspond to these inequalities being strict, but when x is the 0 vector, no matter what a is, this will be 0, so we will exclude that. It's called to be negative definite. If for all x in Rn, but the 0 vector taken out, we have this less than 0, and we say that it's positive definite if we have for all this larger than 0. Well, when we define such things, well, we usually start with positive, but here we started with negative. Well, since although they're dual to each other, we're interested more in maximizing things, where concavity of a function is to the point, and concavity that's actually related to negative semi-definiteness, and we'll see that strict version of that, strict concavity, will be related to negative definiteness. So that's why we started with this. Now this is just a review of quadratic forms, but now we will consider certain theorems which we will use later. Now we will take them without any proofs. The proofs are available in any standard textbook, but in order to motivate what the proofs are, or what the statements, what lies behind those statements, let's consider a simple 2x2 example first. Let A be a symmetric two by two matrix. Well, then symmetry will impose nothing on the diagonal, because xii is equal to xii, no matter what xii is, but these A12 and A21 they have to be equal to each other. Now let us assume that this A is negative definite and try to see whether we can get anything equivalent to that, which is easier to check. So theorems are to simplify life. You don't have to resort to the definition all the time in order to verify that something possesses some property, but if you have some more simplified yardsticks, that makes it easier. Now assume that A is negative definite. Now let's first take any x x1, x2 in R2 and compute explicitly x A x transpose. Now this will be, we will represent x as a row matrix, then we have A, and then we have the transpose of x, which is this column matrix. Now this product will be a 1-by-1 matrix, but we will just consider that as the unique entry it consists of. So we'll have A x1 plus h x2, then h x1 plus b x2. This will be multiplied by x1 x2, and this will be equal to a x1 squared. Then here we'll have h x1 x2, but from here we'll have that as well, so 2h x1 x2 and plus b x2 squared. This is actually the reason why we refer to functions which send each x in R2 to this as a quadratic form. The variables are of degree 2 in all the terms arising. Here you have x1 squared, you have once x1, once x2, and here x2 squared. Let us try to get some information about the entries of the matrix using the assumption that this is negative definite. Okay? Now, consider x1 0, x2 different than 0. Well, then the vector x1, x2, that will be different than the 0 vector. But this will become, as x1 is 0, this will vanish, this will vanish. This will imply that b x2 squared is less than 0. But this will imply, since x2 squared is positive, x2 being different than 0, b is less than 0. So if a is negative definite, then this must be less than 0. But now we can interchange the roles of x1 and x2. Now let's consider x1 different than 0 and x2 equal to 0. This will imply, well, these now will vanish. A x1 squared, that will be less than 0. x1 squared is positive, so a is less than 0 as well. Now let us check what we can, well, these are just two simple extreme cases. Now, this entire expression will be less than 0 when one of the two numbers, x1, x2, is different than 0. Now let's try to rewrite this in such a way that we can get more information about the entries of the matrix. Now, well, when you do that, it will be nice if we can get several terms about whose sign we can deduce something. Well, if you have the square of any real number, then that will be larger than or equal to 0. So it seems promising to complete part of this to a square. Now I can do that as follows. A times, I can factor out a from here, then we'll get x1 squared plus 2h over a, x1, x2. I can do this because a is different than 0, that we know, then plus b x2 squared. Now let's complete this to a square. Well, this looks promising. Then a times x1 plus. Now, for the middle term of the square of the sum to be equal to this, here we need to take h over a x2 squared. Now, if this is expanded, we'll have x1 squared plus 2x1 x2 h over a, which is this, but we'll have one more term, h squared over a squared x2 squared, but that multiplied by this. So let's, to keep the budget balanced, let's take that times x2 squared, and I have this plus b x2 squared. Now I can rewrite this as a times x1 plus h over a x2, and I can write this as, by performing this addition, we'll have ab minus h squared divided by a times x2 squared. This is ab over a, and we'll get this. Okay? Okay, now we know if a is negative definite, this will actually be less than 0 for any non-zero vector x1, x2. Well, let me now choose x1, x2 in such a way that this is squared, I'm sorry, this is squared. Let me make this 0, x1, x2 being different than 0, then we'll get some information from there. So, well, I can take x2 different than 0 and x1 equal to minus h over a times x2. x1 might be 0 because h might be 0, but x2 will be different than 0. Now, set or take x2 different than 0 and x1 equal to the negative of h over a x2. Well, then x1, x2, that will be different than 0, and this expression then has to be less than 0, but this is 0. And we have AB minus h squared divided by a x2 squared less than 0. But this also implies, since this is positive, that we have this. So if A is negative definite, then we have A less than or equal to 0, B less than or equal to 0, and AB minus h squared over A less than 0. But now A is negative. Okay? So if I multiply both sides by A, this will be positive. You'll get 0 here, but A is negative, so the inequality will get reversed. Moreover, this is equivalent actually to A less than 0 and AB minus h squared is greater than 0. Why is that so? If we have the conjunction of these two inequalities, that will imply B is less than 0. Why is that? Well, this will be positive. Well, we know minus h squared is less than or equal to 0, so this has to be positive as well. But since A is negative, that will imply that B will be negative as well. Now, so if A is negative definite, then we have this. But let us go back to the matrix and let us see whether this and this expression have some further meaning concerning the matrix. The matrix was this. Well, in fact, A is the determinant of the 1 by 1 matrix A, and this is the determinant of the entire matrix. But this part was, if A is negative definite, then we have this. Without writing, let us check whether the converse is also true. Let us assume that this holds. Will this imply that this matrix is negative definite? But we know XAX transpose is equal to this. Okay? Now, this will be something non-negative all the time, no matter what x1, x2 is. So this will be negative. Okay? Well, this is negative, this is positive. This will be negative. This x2 squared, well, that will be non-negative. So this expression will be less than or equal to 0 all the time. Well, it still might be 0, but let's check that it cannot be 0. Well, if it's 0, x2 will be 0. Okay, then this part will vanish. This will vanish. We will be left a times x1 squared. But for that to be 0, then x1 has to be 0 as well. So that's not possible. So if this whole expression is 0, then we have shown that x1, x2 has to be 0. Well, if x1, x2 is different than the 0 vector, and this is less than or equal to 0, this will be negative. So in fact, we have shown that A is negative definite if and only if this holds. Now, as you know, this will be true in general for any n by n symmetric matrix. If we extend the notion of this singleton determinant and the determinant of cap A appropriately to the notion of principal minors of a matrix. Now let's define that. Now let A be an n by n, just some matrix. So all our matrices are real matrices, that the entries are real numbers, so I don't write that all the time. For any k in 1 to n, we define the kth principal minor, and that will be denoted by A sub k, as the k by k matrix obtained from A by only keeping the first k rows and k columns. So that means if this is our n by n matrix, now we'll first keep the first row and the first column only. That will be A1. Then this will be A2, and so on. And this principle comes from, as this axis is considered as the principal axis, and the other one as the secondary axis of a matrix. So, well, you could have done the same thing just along the other axis as well. Now, we have our theorem now, which is the generalization of this. Let A be an n by n. Well, this time, since we'll talk about positive and negative definiteness of the matrix, it should be symmetric. An n by n symmetric matrix. Now, A is negative definite if and only if. Well, here, for all k in 1 to n, here the determinant of the 1 by 1 matrix, that was negative, the second one was positive. So they will alternate in sign, and we'll have minus 1 over to the k, determinant ak, that will be positive. Because when k's, if they alternate, when k is odd, they will be negative, but then this will be negative, this will be, and then we'll have this. And We haven't done that, but we could have gone through the same exercise under the assumption that A is positive definite. Then we would get first A and B are positive, and the determinant of the entire matrix is positive as well. So A is positive definite if and only if for all k, this time we have just the determinant of ak being positive all the time. So here we have some characterization of, and some constructive characterization of positive and negative definiteness, because this tells, well, you will just consider n matrices, compute their determinants, and if they obey the inequalities in here, you can decide whether something is positive definite, negative definite, or not. Another theorem, again, let A be an n by n symmetric matrix. Now assume that A is negative semi-definite. Well, and for the second version, positive semi-definite. If we have this information, the question now is, can we check somehow easily whether A is, in the first case, negative definite, and in the second case, positive definite? Now that will turn out to be equivalent to the matrix A being non-singular. Now, A is negative definite, respectively, positive definite, if and only if A is non-singular. Well, one way of expressing that is the determinant of A is different than 0. So as you can see, we have the full characterization and an easy way to decide for the definite versions of here. And here this gives us, well, if you know somehow that the matrix is semi-definite in either sense, you can decide about whether it's definite in the same sense easily by just considering the determinant of A. Well, one might be tempted that if you take this theorem, if you replace these by the semi-definite versions, and if you replace these strict inequalities by weak inequalities, well, that might be a theorem, but that will not. Now let's check some example. Again, a simple example. Is this symmetric? Yes. This is also symmetric because these are just equal to each other. Okay? Now let's consider the principal minors of these. Determinant of A1 Now that's just the determinant of this, that's 0. Determinant of A2, the second principal minor, that's the entire thing. Well, that's 0 as well. Here, determinant of B1, that's just this singleton, that's 0. And determinant B2, that's the entire matrix, that's 0 again. So there is no difference concerning the determinants of the principal minors of these two matrices. If the version of this theorem, just by replacing these by weak inequalities and these by the semi-definite forms, if that were true, then either should these both be negative semi-definite or positive semi-definite or none. But if one has one of the three properties, being positive semi-definite, negative semi-definite, or none, well, the other should share the same property because, okay, so let's check directly for these simple matrices whether these are, in which category these fall. Now, take any x in R2. Now let's check XA, X transpose. This will be X1, X2, then 0, 0, 0, 1, X1, X2. Now this will be the inner product of this with this, that's 0. This, that's x2, so 0 x2 times this is x2 squared. What does this tell about this matrix, 0, 0, 1? Now this will be always larger than or equal to 0. So A is positive semi-definite. It could, of course, be negative semi-definite as well. Well, if XA, XC is 0 for all x, then it's both positive and negative semi-definite. But 0, 1 is in R2 minus 0, and for this 0, 1, A 0, 1, this is 1, 1 squared, so it's 1, this is positive. So A is positive semi-definite, but not negative semi-definite. Let's go through the same exercise for B. Now quickly, XB, X transpose. Well, if you go through this, here you will have minus 1, so this will be equal to minus x2 squared. But this will be less than or equal to 0 for all x in R2. Moreover, this time again, 0, 1 is in R2, and well, for that 0, 1, B 0, 1, this will be equal to minus 1, that will be 0. So B is negative semi-definite, but not positive semi-definite. Thus, they belong to different classes. Well, that means that it is hopeless just to replace this by weak inequality and these by the semi-definite forms. But let us continue with that example. Let me interchange both the rows and columns in here. Make the first row into the second row, and the second to first, and also interchange the columns as well. Then we'll get 1, 0, 0, 0, and for the other, we'll get -1, 0, 0, 0. But this time, the determinant of C1, that's 1. Determinant of C2, that's 0, because that's the entire matrix. Here, determinant of the first principal minor of this, that's -1. Determinant of the second principal, that's the determinant of this, that's 0. Now we have a distinction between these two, and the weak inequalities here in this theorem, they hold and they distinguish between these. So we will modify this theorem by considering all transformed matrices, starting with the given matrix, under some permutation. A permutation on the set from 1 to n, well, that's a 1-to-1 and onto a map from that set onto that set again. So you just change the names, but you change the names of the rows and of the columns according to the same lexicon. And you consider all such matrices obtained via all possible permutations on the set from 1 to n, and you check this and this with weak inequalities, but for all permutations this time. So let's formulate that. A 1-to-1 and onto map from 1 to n onto is called a permutation. On the set from 1 to n. Write S sub n for the set of all permutations on 1 to n. Given an n by n matrix A and a permutation tau in S sub n, we define A tau as the n by n matrix whose ith row, jth column entry is the tau ith row, tau jth column entry of A. That is, if we represent A via the generic form, Aij representing the ith row jth column entry, then A tau, that will be A tau I tau j n by n. Now it is clear that if A is symmetric, then the permuted matrix A tau under any permutation tau on the set from 1 to n, well, that will be symmetric as well. If A is a symmetric n by n matrix, so also is A tau for any permutation tau in S sub n. Now we can write our theorem. Let A be an n by n matrix, symmetric matrix. Now, A is positive semi-definite if and only if for all tau in Sn, we will not just consider kappa itself, but we will consider all permuted forms. Well, cap A, well, tau can be the identity map. Well, in that case, A tau will be A, so A will be considered as well. And for all k from 1 to n, this is positive semi-definite, so the determinant of the tau of the kth principal minor of the tau permuted matrix, that should be larger than or equal to A, and A is negative semi-definite if and only if for all permutations for all k, this time minus to the power k, determinant of A tau k that is larger than or equal to 0. Okay? So that's our short and quick review of quadratic forms. Well, we can now guess why we did this, because we have the last version of characterizing concavity or convexity of a function. In the one-dimensional case, well, if the function is twice differentiable, f double prime on its domain, that should be less than or equal to 0 everywhere. That was equivalent to concavity. For strict concavity, it will be one-sided. We mentioned that, but we'll come back to that. So we need the counterpart of the second order derivative. We have just the first derivative in the general case. So we need the second derivative. But we do not expect the second derivative to be just one real number. It will again be a function. In a sense, not a linear, not a unary form, but a quadratic form. Not exactly a quadratic form, but at its crucial points, it will turn out to be a quadratic form. It will be represented, again, by an n by n matrix. It will be representable by an n by n matrix, the second derivative. But that matrix being negative semi-definite, that will correspond to Q double prime being less than or equal to 0, and that being positive semi-definite, that will correspond to Q double prime being larger than or equal to 0. So next hour, we'll define higher order derivatives of a function. Well, this time on Rp with values in R, and we will not define it in the most general form. Well, we will just take the version in terms of partial derivatives that we would get if we went through all the job that we did in the first derivative, but that representation in terms of partial derivatives we will take as our definition and then extend f if differentiable is concave on its domain, if and only if the second derivative of the function is less than or equal to 0, and the other way around for convexity. But let's first have a break.